Here are our solutions to homework set number 1 for ECE 376. This homework is really just a background on the PIC processor. What are the capabilities of a PIC? How much current can it drive? You can measure voltage to 4.88 millivolts. What does that mean? You can measure time to 100 nanoseconds. What does that mean? So the first page is just kind of a summary. Let's go through the problems one by one. The first problem is, how many clocks does it take to do an integer operation in C? Well, if you go to Bison Academy, you can look at old homework sets and solutions from homework 9, spring 24. We calculated that. Turns out here's the solution from spring 24. It was 197 clocks, or 19.7 microseconds, to do an integer operation. Problem 2. The output pins on a PIC are limited to 25 milliamps. What that means is, from V equals IR, I can drive a resistance of 200 ohms or more. What that means is, if I have an 8 ohm speaker that I want to drive, I can't drive that directly from a PIC. A PIC can't drive 8 ohms at 5 volts. 5 volts at 8 ohms is 625 milliamps. If I want to do that, I need to add a 200 ohm resistor in series, which is 192 ohms, because of 200 ohms. That limits the current, saves the PIC. That's going to give you a really quiet speaker. Another option is I could add a buffer circuit. This is something we're going to cover a little bit later. This is what you do in electronics. I'll add a buffer. That's a transistor or an H-bridge. That then drives the speaker. But I can't drive it directly. Problem 3. Suppose I can measure voltage to 4.88 millivolts. So here I've got a voltage divider. If this is 2.2K nominally, and that resistor changes, as R changes, the voltage changes. The smallest change in voltage that I can see is 4.88 millivolts. What's the smallest change in resistance I can see? Well, to figure that out, I'll first take the nominal voltage. When this is 2.2K, I get 2.5 volts. That's nominal value for V1. If I change V1 by 4.88 millivolts, it becomes 2.50488 volts. Now find R2. Doing some algebra, R2 winds up being 2208 ohms. So to go from 2200 to 2208, difference of 8.606 ohms. That's the smallest change in resistance that I can measure using the analog input on a PIC and the circuit. If this is a temperature sensor, like a thermistor, as temperature goes up, resistance changes. Here's the equation. The nominal, if it's 2200 ohms at the nominal temperature is, solve, you get 8.08 degrees Celsius. If temperature changes, R changes. If R changes, voltage changes. The smallest voltage change I can see is 4.88 millivolts, or 8.606 ohms. In terms of temperature, make this 2208.606 ohms, solve for T, I get 8.0083 degrees C. The difference in temperature is your resolution. The difference is 0.079 degrees Celsius. I can measure temperature with a resolution of 0.079 degrees Celsius with the analog input. So that's one way to have inputs. You can have the A to D input reading voltage. Another thing a PIC can do is can measure time. Computers are really good at measuring time. For the PIC, 1 clock is 100 nanoseconds. To give an idea how small that is, Quicksilver, the fastest of the X-Men, can run 175 miles an hour in 1 clock, converting miles an hour to meters per second, multiplying by 100 nanoseconds. Quicksilver travels 7.8 microns in 1 clock. Human hair is about 180 microns, so this is less than the size of a human hair. A bacteria is about 1 micron. So that's a really tiny number. If I have a 555 timer, what the 555 timer does is I charge through R1 and R2, discharge through R2. So you have the voltage right here is doing charge, discharge, charge, discharge. This is an oscillator with the 555 timer. The output is a square wave. While I'm charging, it's high, discharging low, charging high, discharging low. I get a square wave. And the square wave is related to R and C by this equation. If these are nominally 2200 ohms, 2200 ohms, 0.22 microfarads, the period is 1.06 milliseconds. So this guy right here is 1.0064 milliseconds. Or, flipping it, 993 hertz. The smallest change in frequency I can detect is if the period increases by 1 clock, 100 nanoseconds. So if I increase this by 100 nanoseconds, then find the frequency, the difference in frequency is 0.0987 hertz. So a PIC can actually tell the difference between 993.59 hertz and 993.49 hertz. You can see that that's the difference of 1 clock. If I take that resistor, so I've got this circuit on the left side of the 555 timer. If this resistor varies, R2, if R2 varies, the time varies. How much can R2 vary for the period to change by 100 nanoseconds? So nominally, the period is 1.006 milliseconds. If I add 100 nanoseconds, it's 1.0065 milliseconds. Plugging that in over here, I know R1, I know C, I know log of 2, solve for R2. If R2 changes from 2200 ohms to 2200.32 ohms, I can see that. That causes the period to increase by 100 nanoseconds. Meaning, I can now measure resistance to 0.3 ohms. Now compare. Before I could measure resistance to 8 ohms, I can now measure resistance to 0.3. If I can convert something to time, I can measure it really accurately with a PIC. And it could actually do better. I don't have to measure every cycle. I could increase C and make the period longer. I could count 16 cycles, get even better resolution. I can measure really accurately if I convert to time. If I make this resistor a thermistor, their resistance is a function of temperature. Nominally, the temperature is 8.08 degrees when I'm at 2200 ohms. If I plug in this for R, the smallest change in R I can see, solve for T. The difference is the smallest change in temperature I can see. I can now measure temperature to 0.0029 degrees Celsius. Really accurately. So that's homework set number 1. With a PIC, it's not the newest processor in the world, it's not the most powerful processor in the world, but it's really darn impressive. With it, I can measure temperature to 0.0029 degrees Celsius. I can measure resistance to 0.3 ohms, 2200, measured to, 5 decimal places. It's really quite capable processor. So that's what we're going to be using for the rest of the semester. Have respect for it. It's actually quite powerful. And that's homework set number 1 for ECE 376.